In Chapter 9 we will study relations. We will start by defining a binary relation. The definition here is a binary relation R from a set A to a set B is just a subset of A cross B, the Cartesian product of A and B. Here's an example. A has integers 0, 1, 2. B has the letters A and B. Any subset now of A times B will be a relation. For example, if you take the ordered pairs 0A, 0B, 1A, 2B, this is an example of a relation from the set A to the set B. We can represent relations from a set A to a set B graphically or using a table. The graph in the left, you can list the elements of set A to the left as dots or vertices, and you can list the elements from B to the right, and then anytime you have an ordered pair from an element from A, if you have an ordered pair with the first element from A and the second element from B, you can draw an arrow from the first element to the second element. The other way to do it is using a table like the one we see. You can include the elements of the first set in the column 0, 1, 2, and you include the elements from the second set in the row A and B. But anytime you have an ordered pair, for example 0 and A is included in the relation, so you use X, write an X. If the two elements are not related, just leave it blank. And we will see more ways to represent a relation. Relations, of course, are a generalization of the idea of a function. It turns out that a function is a relation. You can think of it as a subset of the Cartesian product of the domain and the codomain. A function is a special relation. There are certain conditions that must be satisfied. But the idea of a relation is a more general idea. Now, if the first and second sets are the same, you can define then a relation on a set. The binary relation R on a set A is just a subset of A times A. It's a relation from A to itself. For example, if A has the letters A, B, and C, here's an example of a relation on A. The relation that contains ordered pairs AA, AB, AC is an example of a relation on A. Here is another example. If A is a set that has the integers 1, 2, 3, 4, the ordered pairs in the relation now is defined to be the set of all ordered pairs A, B, such that A divides B. The first element divides the second element. But for that set, you can actually list all these elements. 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, and 4, 4. These are all the related elements. Here, in every ordered pair, the first number divides the second number. Here is the same relation. A is the set that has the integers 1, 2, 3, 4. For which ordered pairs are there in the relation A, B such that A divides B? We already listed all the elements in the previous slide. You can list all the ordered pairs that satisfy this condition. The other way is to describe the relation using set builder notation by writing R is the relation AB such that A divides B. You can use graphs. either use this graph which we used before. The same set is listed as the starting set and the second set. Anytime an integer divides from the set divides another one, you draw an arrow to indicate that it divides the second integer. طبعا another يعني directed graph that can be used, you just list the elements one time and يعني draw an arrow every time a number divides another number. Draw an arrow from the first number to the second number. طبعا in the second graph you see loop. These are called loops. These are arrows from the integer to itself. طبعا that would indicate if every integer in that set divides itself. We will يعني see many relations يعني using graphs. To be more accurate, these are directed graphs, is one way to represent relations. طبعا احنا we looked at the idea of using a table to represent the relation, and that should give us an idea to use a matrix. Actually, the preferred way to represent the relation is using a matrix. Looking at the table, طبعا this is a relation on the set. For the elements of the set are listed in the top row and in the first column. Now يعني in the first row you see x's. This would indicate that one divides every other integer in the set except itself. The second row there's an x. 2 divides 2 and 2 divides 4. The third row 3 divides itself and nothing else, and 4 also divides itself and nothing else. Now these, if you replace those x's by 1 to indicate that the integer divides, and the blank replace it by 0, you get a 0 and 1 matrix. Yani list the elements of the set in the top row and in the column outside the matrix, and then طبعا 1 here would indicate that an element from A divides the other element, and an element of the column divides the element in the row. So 1 would indicate it divides, and 0 would indicate that it does not divide. بس يعني طبعا when you are forming the matrix, it might be helpful to list the elements on top. يعني list 1, 2, 3, 4 on top of the matrix, and list 1, 2, 3, 4 again in the column. And then anytime a number from the column divides a number from the row, just record 1, and if it doesn't divide it, then record 0. But this is another application of using zeros and 1 matrices. This is يعني one way to يعني define a relation on the set by using a matrix. Here are more examples, and يعني a relation can always be written as describing the relation. If you have a finite number of elements, you can also list all the يعني ordered pairs in the relation. Here are more examples. The set A has the numbers -1, 0, 1, and 2. These are 3 different relations, and يعني we will look at some of them and list all the elements يعني in the relation. For example, R1 يعني consists of all the pairs where A is less than B. These are the ordered set in R1, يعني -1, 0, -1, 1, -1, 2, 0 and 1, 0 and 2, 1 and 2. But these are all the ordered pairs where the first element is less than the second element. The second relation, A is related to B or AB is in the relation if one of the conditions hold. Either A equals to B, or A is equal to B, or A is equal to -B. Yani if one of the conditions holds. For example, R2 then might include -1, -1, 0, 0, 1, 1, 2, 2. In these ordered pairs, A is equal to B. طبعا the second condition, A is equal to -B, is satisfied with -1, 1, and 1 and -1. But these are all the ordered pairs in R2. R3 contains all the ordered pairs where the sum of A and B is larger than or equal to 0 and less than or equal to 1. This would include now the ordered pairs minus 1, 1, 1 and minus 1, minus 1 and 2, 2 and minus 2, 0, 0, 0, 1, and 1, 0. These are all the ordered pairs that satisfy the given condition. Here is a counting problem. How many relations are there on a set with n elements? طبعا to answer this, you know a relation on A is just a subset of A times A. How many elements does A times A have? It has n squared element. We want to count the number of relations. We count the number of subsets of A times A. طبعا the number of subsets of A times A, since it has n squared element, is 2 raised to the power n squared. But there is 2 raised to the power n squared relations on the set of with n elements. Here is an example. If S has letters A, B, C, so n is equal to 3, then the number of relations on S is 2 raised to the power 3 raised to the power 2. Yani 2 to the 9, or 512 relations. There are special relations. One is the identity. This is the identity on a set A. This is the set of all ordered pairs AA. Yani the first element equals the second element. By the way, if you use a matrix to represent this relation, this relation will have 1s in the diagonal and 0s everywhere else. This is طبعا one special relation. Here is an example for A contains the integers 1, 2, 3, and 4. Here is a list of all the ordered pairs in the identity: 1, 1, 2, 2, 3, 3, and 4, 4. Now we're ready to study some of the properties of relation. The first property is reflexive, or reflexivity, and there is another property that's related to it called irreflexive. We will see what reflexive means and what irreflexive means. A relation is reflexive if A is in the relation for every element A in the set A. In other words, that every element in the set A is related to itself. Here is an example. The set here, A has the numbers 1, 2, 3, 4. Here is a relation. This relation is not reflexive because it does not include the ordered pairs 3, 3. Yani 3 is not, yani 1, 1 is there, 2, 2 is there, but 3, 3 is not in the relation, but the relation is not reflexive. The same relation, I think, if you just on R2 here you find 1, 1, 2, 2, 3, 3, and 4, 4. Every element is related to itself, then it is reflexive. Now, what is irreflexive? Irreflexive means that for every A in the set AA is not an R. Yani no element is related to itself. Yani to check that a relation is reflexive, you have to make sure that the ordered pair AA is in the relation for each A. Yani every element related to itself. To check for irreflexive, no element must be related to itself. That means AA is not an R for any A. Yani no element is related to itself. Here is an example. R3, here is a relation that's not irreflexive because it has 1, 1. It is not irreflexive. This is an important note that irreflexive does not mean not reflexive. These are not opposite properties. Yani a relation, if you have a relation where some of the elements are related to themselves but not all, then the relation is not reflexive. At the same time, it is not irreflexive. You have to be careful. And irreflexive does not mean not reflexive. Here are examples of reflexive relations. R1 is the set of all ordered pairs A, B such that A is less than or equal to B. The second relation, which we looked at before, A, B such that either A equals B or A equal minus B, and the identity R3 is the identity A, B such that A equal B. All of these are examples of reflexive relations. There is, of course, one other special relation, which is the empty relation. And again, if you take any subset of A times A, that will be a relation on A. In particular, if you take the empty set, this is a relation on A. This relation will be reflexive by default. There is nothing to check. The empty relation on an empty set is reflexive. Here are examples now of relations that are not reflexive. R4, the set of ordered pairs A, B such that A greater than B. It's not reflexive, in fact it will be irreflexive. For example, 3 is not larger than 3, and 3 is not related to itself. In fact, this particular example will be an irreflexive relation. The second relation that's not reflexive, if you take the ordered pairs A, B such that A equals to B plus 1. A is the next integer. If A equal B plus 1. But here again 3 is not related to 3 because 3 does not equal 3 plus 1. This is not reflexive. Here is one more. R6, A, B such that A plus B is less than or equal to 3. The number 4 is not related to itself. Then 4 plus 4 is not less than or equal to 3. All of these are examples of relations that are not reflexive. The next feature or property is symmetry, or we say the relation is symmetric, and the feature that's associated with it is antisymmetry. If a binary relation R on a set A is symmetric, if this condition holds, AB is in the relation if and only if BA is in the relation for any A and B in the set A. Anytime A is related to B, then also B must be related to A. And that has to be true for all AB in the set A. Here is an example on the same set that we used now so many times, the set that has the integers 1, 2, 3, 4. R1 is a relation that's symmetric, then for each ordered pair, if AB is in the relation, then BA is also in the relation. You can check that, you have to check each ordered pair, but the relation is symmetric. The other property is called antisymmetric, and the way, the condition for that is that AB is in the relation, means BA is not in the relation. If A is related to B, then we must have, and B is not related to A. In a symmetric relation, the only time where you could have AB in the relation and also BA in the relation if A equals to B. That's the only case, if A and B are the same elements, that's the only case where you have A is related to B and B is related to A. This is for a symmetric relation. Antisymmetric relation. Here is an example. How do you check for antisymmetry? Check for every A, B in the relation. Make sure that BA is not in the relation unless A and B are the same elements. This is true for R2. R2 has the ordered pairs 1, 1, 2, 1, 2, 2, 3, 3, and 3, 4. It satisfies the condition for antisymmetry, that if A, B is in the relation, then BA is not in the relation. Here are more examples of symmetric relations. We have seen these before. R1 is the ordered pairs A, B such that A equal B or A is equal to minus B. This will be a symmetric relation. R2 is A, B such that A equals B. This is identity. R3 is a set of ordered pairs A, B such that the sum is less than or equal to 3. It is easy to show that these relations are symmetric. Here is examples of relations that are not symmetric. A, B such that A is less than or equal to B. This is not a symmetric because, for example, 3 is less than or equal to 4, and 3 is related to 4, but 4 is not less than or equal to 3. 4 is not related to 3. This is not symmetric. I think this one will be antisymmetric. Here is another one, A, B such that A is greater than B. This is not symmetric. 4 is related to 3, and 4 is greater than 3, but 3 is not greater than 4. And the other relation that we have seen before, A, B such that A is equal to B plus 1, this is not symmetric. For example, 4 is equal to 3 plus 1, yani 4 is related to 3, but 3 is not related to 4. 3 does not equal 4 plus 1. All these are examples of relations that are not symmetric. Here are examples of relations that are antisymmetric. R1 is A, B such that A is less than or equal to B. R2 is A, B such that A is greater than B. The identity relation. R3 is the identity A, B such that A equals B. Remember now, the identity, which is R3, was an example of a symmetric relation, and it is also antisymmetric. A relation can be both symmetric and antisymmetric. طبعا يعني it is not difficult to see because all the ordered pairs have the form A equal B, but the condition is satisfied that A is related to B and B is related to A when A is equal to B, or A is equal to B for all the ordered pairs. But this is a relation, يعني at least now you know, and a relation can be symmetric and also antisymmetric. R4 is the relation A, B such that A equal B plus 1. This is also antisymmetric. And if A is related to B, then B is not related to A. Here are examples of relations that are not antisymmetric. R5, A, B such that A equal B or A equal minus B. These are not antisymmetric. In fact, we have shown that they are symmetric. For example, these are not antisymmetric because 1 is related to minus 1, and also minus 1 is related to 1. Anytime you have a symmetric relation that's not empty, then it will not be antisymmetric. Then this is an example of a relation that's not antisymmetric. R6, A, B such that A plus B is less than or equal to 3. Here both 1, 2 and 2, 1 belong to R6, but the relation is not antisymmetric. In this case also, this relation was an example of a symmetric relation. Anytime you have a relation that is symmetric and not empty, then it will not be antisymmetric. Here are quick examples. We have limited time, so we will not check everything here. But here the underlying set is 1, 2, 3. All of these are relations on A. The first one, R1, is an example of a relation that's not reflexive. طبعا not reflexive because 1, 1 is not there. It is not irreflexive because 2, 2 is there. The second example, for that R1, it's not reflexive, it's not irreflexive. Not symmetric because 2, 1 is not in the relation. not antisymmetric because both 3,1 and 1,3 is in the relation. R2 is not reflexive, that's very clear, and the 1,1 is not there. Not irreflexive because 1,3 is in the relation. Okay. طبعا for an irreflexive relation, no element should be related to itself. 1,3 is in the relation, so it's not irreflexive. R3 is an example of a relation. This is identity, so it's reflexive. It is not irreflexive. It is symmetric and antisymmetric. We already stated that in the identity relation on any set is an example of a relation that is symmetric and also antisymmetric at the same time. R4 has only one ordered pair, 2, 3. It is not reflexive, that should be clear. It is irreflexive. It is not symmetric because 3, 2 is not there, and it is antisymmetric. The third property for relations is called transitive. You say a relation is transitive if and only if for all A, B, C, if A is related to B and B is related to C, then A must be related to C. This is called the transitive relation. طبعا maybe the best example for a transitive relation is the division. One of the rules we studied when we studied division, that if A divides B and B divides C, then A divides C. But that's an example. The division relation is an example of a transitive relation. Here are more examples. For the set A that has the integers 1 and 2, R1 here will be transitive. طبعا you actually have to check for every possible A, B in the relation and B, C also in the relation. You must show that A and AC is also in the relation. طبعا this is a finite number of ordered pairs. It should be easy to verify the condition. R2 is not transitive. You see that 2, 1 is in the relation and 1, 2 is in the relation, so you must have 2, 2, which R2 does not include 2, 2. Okay, then it is not transitive. R3, which contains only one ordered pair, 3 and 4, is transitive by default. Here are more examples of transitive relations. R1 is AB such that A is less than or equal to B. R2, AB such that A is greater than B. R3, AB such that A equals B or A equal minus B. R4, AB such that A equal B, which is the identity relation. All of these are examples of transitive relations. Here are examples of relations that are not transitive. R5, AB such that A equal B plus 1. This is not transitive, and it should be clear that 4 is related to 3 and 3 is related to 2, but 4 is not related to 2. The transitivity condition is not satisfied. Here is a counterexample. The other example of a relation that's not transitive is AB such that A plus B is less than or equal to 3. It is clear that 2 is related to 1 and 1 is related to 2, but 2 is not related to 2. The special case we already mentioned, the empty set is the special case. This is a special relation. This is a relation that has no ordered pairs. Nothing is related to anything. Most conditions now will be satisfied by default. For the relation is considered to be irreflexive, transitive, symmetric, and antisymmetric. The other special relation is a universal set. Take all the ordered pairs in A times A. For everything is related to everything. This is a universal set, is a relation. It will be reflexive, transitive, and symmetric. Now, combining relations, when you think of a relation being a subset, يعني a relation from A to B is just a subset of A times B. So you can combine relations by taking the union, intersection, and set difference, and that will give you another or a new relation. Here is an example. A is a set that has integers 1, 2, 3. B is a set that has 1, 2, 3, 4. R1 is an example. R1 and R2 are examples of relations from A to B. R1 union R2 is just a new relation from A to B that consists of all the ordered pairs that are either in R1 or in R2, and they are listed in the slide. The intersection is the ordered pairs that are in both in R1 and R2, and there is only one element, one ordered pair, which is 1, 1. The set difference are those ordered pairs which are, here we are forming R1 minus R2, but this is a set of ordered pairs that are in R1 but not in R2. And there's only two ordered pairs, 2, 2, and 3, 3. The other way that you can form new relations is composite relations, yani forming the composition of two relations. The way that you define composition, if AC is in R1 and CB is in R2, then take AB to be in the composition, R2 circle R1. Here طبعا order is important, but you're starting with R1 and then you apply R2. يعني AC is in the first relation, R1. CB is in the second relation, R2. Then the first element from the first ordered pair and the second element from the second ordered pair, AB, must be in the composition, R2 circle R1. Here is an example. R is a relation from the set 1, 2, 3 to 1, 2, 3, 4. And here are the ordered pairs from the relation. S is the relation from the second set, 1, 2, 3, 4, to the set 0, 1, 2. Now the composition will be a relation from the first set to the third set. And it will be a relation from 1, 2, 3 to 0, 1, 2. For this is طبعا S, these are the ordered pair in S. The composition, what you want to start is check for every AC in the first relation. يعني for each AC, look for elements in the second relation, CB, and include AB in the composition. For example, if we do some of these, يعني start with 1, 1, pick every element ordered pair that starts with 1, and include the first element from the first ordered pair and the second element from the second pair. So with 1, 1, you have to take 1, 0, then 1, 0 is in the composition. For 1, 4, look for ordered pairs in S that start with 4. We have 4, 1, take 1, 1. For 2, 3, look for elements that start with 3. You have two elements, so you must include 2, 1, and also include 2, 2. For 3, 1, you have 3, 1 in R, 1, 0 in S, so you must take 3, 0. The final element, 3, 4, 3, 4 in R, 4, 1 in S, so take 3, 1 in the composition. يعني those ordered pairs now will be a relation from the first set 1, 2, 3 to the third set, which is 0, 1, 2, defined by these ordered pairs. And طبعا this is يعني the composition is formed by construction. You have to actually يعني take every pair in R and يعني perform the composition in the manner that we explained. The other thing you can do is powers, and now powers are done for relations on a set A. The power R, يعني R, the relation R is a relation on set A. For R to the n must be a positive power, positive integer, 1, 2, 3. For R1, R to the power 1 is just the relation you start with, R. R to the n is equal to R to the power n minus 1 composed with R. Yani this is by construction. Start with R1, which is the relation you start with, and then the next power would be the previous power composed with R. Here is an example. R has the ordered pairs 1, 1, 2, 1, 3, 2, 4, 3. For R squared is just R composed with itself, and this is what you get, 1, 1, 2, 1, 3, 1, and 4, 2. What about R3? R3, just take R2, compose it with R, and here is the ordered pairs you get, 1, 1, 2, 1, 3, 1, and 4, 1. For every power, just take the previous power and compose it with R. you can do this طبعا. The powers work only if the relation is on a set. It's a relation from A to A. Representing relations, we have already seen some methods to represent a relation. You can represent a relation by using 0, 1 matrix or with a directed graph. We actually have seen both methods, but we will see more examples now. To represent a relation using a matrix, طبعا, you can take the set A. This is a relation now from A to B. So you can list the elements of A, the first set, in a column, list the elements of B in a row, and now for every element, every time you have an element from A related to an element from B, you must record 1. That means they are related. If an element from the column is not related to an element in the row, then you must write 0. But we have seen this method before. طبعا the matrix that you get by this method is the matrix that represent the relation. Here's another example. The relation from the set A that has the numbers 1, 2, 3 to the set B which has the numbers 1, 2. Here is a relation now from A to B that includes the pairs 2, 1, 3, 1, and 3, 2. List the first set in the column 1, 2, 3. List the second set in a row above the matrix 1, 2. طبعا anytime you have 0, that means the two elements are not related. If you have a 1, that means then the element in the column is related to an element in the row. This is now the resulting matrix that represent this given relation. The matrix that represent R is the matrix that we got by performing this representation. 1 means the two elements are related, 0 means the two elements are not related. And we can write, this is the matrix, and we can write the name of the relation. This is the matrix that represent R. طبعا you can tell some of the properties. This is when you have a relation on a set. Some of the properties you can tell from the matrix. For example, if you have 1s in the diagonal, then that means every element is related to itself, so the relations is reflexive. If you have 0s in the diagonal, that means none of the elements is related to itself, so the relation is irreflexive. If you have 1s across the diagonal or 0s across the diagonal, that means every time A is related to B, then B is related to A, and that's just symmetric. For all identical across the diagonal. Antisymmetric, every time you have 1, then across the diagonal you will have 0. That means if A is related to B, then B is not related to A, and that is antisymmetric. Certainly then some of the properties of the relations you can tell from the matrix that represent the relation. Here is an example for the relation that's represented by this matrix. The relation will be reflexive because it has ones in the diagonal. It will also be symmetric because you have ones across the diagonal. And it is not antisymmetric, لأن to be antisymmetric طبعا you must have zeros across the diagonal from ones, which we don't have in this relation. But the relation will be reflexive, symmetric, but not antisymmetric. Now what about we were able to form new relations by taking unions and intersections. You can actually use the operations we studied on 0 and 1 matrices can be applied, which is join and the meet. You can use them to find the matrices for the union and intersection. For example, if we know the matrix that represent R1 and R2, then the matrix representing R1 union R2 is just the join of the matrix for R1 with the matrix for R2. The matrix for the intersection of R1 and R2 is just the meet of the matrix for the first relation and the matrix for the second relation. Here is an example. R1 and R2 are relations on a set A represented by the given matrices. Here is the one to the left is the matrix for R1 and the matrix for R2 is in the right side. If I want the matrix for the union, R1 union R2, just take the join of the matrix for R1 with the matrix for R2, and here is the result. The matrix for the intersection, R1 intersected with R2, is just the meet of the matrix of R1 with the matrix for R2. And here is the result for the meet, which is the matrix for the intersection. One more thing, طبعا we also have the relation which is the composition. You can use the operation, the Boolean product, to find the matrix for the composition. If R is the relation from A to B and S is the relation from B to C, then to find the matrix for S circle R and the composition of S and R, just take the Boolean product of the matrix for R with the matrix for S. Now the order here is important. If you want the matrix for S circle R, the composition of S and R, start with the matrix for R, because that's the relation you apply first. For the matrix of R, multiplied Boolean product with the matrix for S. Here's a relation, or two relations, the matrix for R, the matrix for S. If I want the matrix for the composition S circle R, I must do the product, the Boolean product of the matrix for R with the matrix for S. If you check, the Boolean products of these matrices should give you this given matrix, which is the matrix that represent the composition of S and R. Now what about powers? It works the same way, and you are applying Boolean products where you end up with Boolean powers. But the matrix for the relation R to the n is equal to the matrix for R. It is the nth Boolean power of the matrix for R. You multiply, if you want the matrix for the relation R to the n, just multiply the matrix for R by itself n times. For example, R2 is just the composition of R with itself. For the matrix for R squared is just the matrix for R, the second Boolean power for the matrix for R. R3 is just the composition of R2 with R, but the matrix for R3 is just the third Boolean power of the matrix for R. Here is an example. The matrix that we want the matrix for R2. If we know the matrix for R, the one to the left is the matrix for R. If I want the matrix that represent the relation R squared, this is just the second Boolean power for the matrix for R. Take this matrix, multiply it by itself, Boolean product, The result, which is the second Boolean power of the matrix for R, will give you the matrix for the relation R squared. The other way which we have seen is using directed graphs. Here is an example. طبعا the directed graph, you have a relation from A to B. Use a directed graph anytime you have an ordered pair from A to B. Then you represent that by 1. If the two elements are not related, then use 0. You can tell some of the properties of a relation from the digraph. For example, if a relation is reflexive, then every node has a self loop. And the self loop will tell you that the element is related to itself. If in a reflexive relation, every element is related to itself, so there will be a loop. Irreflexive, that means no node links to itself. That means you don't have any loops, because no element should be related to itself. Symmetric, that means every link is bidirectional. Then if A is related to B, then B must be related to A. Every time there's an arrow from A to B, there should be an arrow from B to A. Antisymmetric, no link is bidirectional, and you don't want A related to B and B related to A. But there will not be any links that are bidirectional. The closure of relations for any property. Now we have seen, for example, with the property of being reflexive, to be reflexive, you need every element to be related to itself. Sometimes many of the elements are related to themselves, but not all. The idea of the closure of a relation is that if there are missing ordered pairs, you can add those ordered pairs until the relation has that property. In general, for any property X, the X closure, for example, the reflexive closure or the symmetric closure, the X closure of a set A is defined to be the smallest superset, so it will be a larger set. It is the smallest superset of A that has the given property. For example, the reflexive closure would be the smallest superset that contains the relation that is reflexive. One way to find the reflexive closure that you can add AA to R for any A in the set A that is not already there. And you just add the missing pairs. Just add AA to the relation for each A that's not already for any A in the set A where AA is not there, you just add that ordered pair. Another way to look at that is just take an R union the identity. That will guarantee the result will be a reflexive set, and that will give you the reflexive closure of A. Here is an example. The relation which has the ordered pairs 1, 1, 1, 2, 2, 1, 3, 2 on the set 1, 2, 3 is not reflexive. 1, 1 is already there, but there is two pairs that are missing, 2, 2 and 3, 3. But to get the reflexive closure, start with the relation R and add the missing pairs, add 2, 2 and 3, 3. This is the smallest superset. This is the smallest relation that contains the original relation, and it is reflexive. But that's the reflexive closure of R. Here is another example. For the relation A, B, such that A is less than B, this is far from reflexive. This is in fact irreflexive. If I want the reflexive closure, I have to add all the ordered pairs AA for A and Z. Basically, I'm adding the identity. You end up then with the relation AB such that A is less than or equal to B. That is the reflexive closure of R. The symmetric closure is done the same way. The symmetric closure of R is obtained by adding BA to R for each AB in R. And I check for every AB in R, make sure that BA is there. If it's not, then you add it. The result now will give you the smallest possible relation that contains the original relation, but the closure now will be symmetric. Another way to form the symmetric closure is taking R union R inverse. R inverse, the inverse of a relation is just invert the order of the ordered pairs. But if you take the union of R with its inverse, that will give you the symmetric closure. Here is an example of a relation 1, 1, 2, 2, 1, 2, 3, 1, 2, 3, and 3, 2. This is a relation on 1, 2, 3. It is not symmetric. What is missing? 1, 2 is in the relation, but 2, 1 is not. 3, 1 is in the relation, but 1, 3 is not. The other pairs are okay. But then the symmetric closure, take the relation you start with and add the missing pairs, which in this case they are 2, 1 and 1, 3. The result now is the smallest relation that contains my original relation, but this relation now will be symmetric. So that's the symmetric closure of R. Here is an example, another example. R is the relation AB such that A is greater than B on the set of positive integer. What you need to do is take the union with the inverse for AB such that A is greater than B, union BA such that A is greater than B. In the first relation, the original relation, the first element is larger than the second element. Take the union of that with the inverse, so you're taking all BA where the second element is larger than the first element. So the result will give you the symmetric closure. But that's just all the ordered pairs AB, with the exception where A is equal to B. And you're taking everything AB that either A is larger than B or B is larger than A. And that will give you the symmetric closure of the original relation. Transitive closure is done the same way. The idea is that you want to be sure that the transitivity condition is satisfied. Anytime you find AB in the relation and BC, you must add AC if it's not already in the relation. You want to make sure that the condition for transitive is satisfied. You keep adding AC. Anytime you find AB and BC in the relation, you must add AC. Another way to form the transitive closure, this is R star. Take the union of R to the n for every possible n, every positive integer. There will be a limited number of these relations that you're taking the union. You can also do it in terms of 0 and 1 matrices. The matrix for the transitive closure is just the join of all the powers for the relation. You take the matrix of R joined with the matrix for R squared. If you take the join of all those matrices, that will give you the matrix of the transitive closure. Or the other way, if you have a small relation, you just try to apply the condition directly by adding AC to R. Every time you see AB and BC in R, you must add AC. Here is an example using the union of powers of R. This is the relation now on the set 1, 2, 3. For R star, you only need to take the first 3 powers, and A has only 3 elements. For the transitive closure, you can get the transitive closure by taking R union R squared union R to the power 3. You must form first of all find R squared by composing R with itself, and then form R to the power 3, and that's just R squared composed with R, and then R star is just a union of those three relations. This will give you, this is a relation now that is a transitive closure. Or طبعا you can do it by inspection, يعني just look what's missing for the relation to be transitive. You have 2 1 and 1 2, so you must include 2 2. You add 2 2. Also you have 3 2 and 2 1, so you must include 3 1. If you just add those two ordered pairs to the original relation, the result will be a transitive relation. So then this is the transitive closure. Or of course you could use the union of the powers of R. It just might take a longer time, but you get the same result. Also, if you another option is to use the matrices. This is for the same example. This is a matrix for the relation R. But now the matrix for the transitive closure would be the joint of the matrix for R with the matrix for R squared with the matrix for R3, R to the power 3. And again, this just takes more work. At least in this example, the easiest way to form the transitive closure is just do it by inspection, by adding the missing pairs. Next, we would like to define equivalence relations. Equivalence relations are relations that satisfy the three conditions. The relation must be reflexive, symmetric, and transitive. Here is an example of an equivalence relation. The relation here is defined by AB such that A minus B is an integer. I mean, this is a relation on the set of real numbers. To show it's an equivalence relation, we must show that it is a reflexive, symmetric, and transitive. طبعا any real number A, if you subtract A minus A, you get 0, which is an integer, for A is related to A for all A. The symmetric property, if A is related to B, then A minus B is an integer. So if you multiply this by minus 1, you still have an integer. معناتها B minus A is also an integer, which means B is related to A. That is a symmetric property. Transitive, if A is related to B and B is related to C, that means A minus B is an integer, and also B minus C is an integer. If you add two integers, you will get an integer. So the sum here will be just A minus C is an integer, so A is related to C, and that is the transitive property. Okay, then the relation R is reflexive, symmetric, and transitive, so it is an equivalence relation. Here is another important equivalence relation, which we already considered when we studied the integers, and that is the equivalence of the congruence relation. The congruence mod M is an example of an equivalence relation. It is a relation on the set of integers, and that is defined by A and B is in the relation, or A is related to B, if A is congruent to B mod M. M, of course, is a positive integer greater than 1. This is an equivalence relation. طبعا just to remind you, one way to check for congruence, that A will be congruent to B mod M if M divides A minus B, or A minus B is divisible by M. That's the quickest way to check for congruence. For reflexive here, M divides A minus A, or A minus A is divisible by M, but then A is congruent to A for all A. Every element, every number, every real number is congruent to itself mod M. Symmetry is easy. If A is related to B, then A minus B is divisible by M. If you multiply that by minus 1, you still get a number that's divisible by M. But then B minus A is divisible by M, or B is related to A. Transitive, if A is related to B, A is congruent to B, and B is congruent to C, then M divides A minus B and also divides B minus C. So it must divide their sum. Their sum is just A minus C. That means A minus C is divisible by M, or A is related to C. So that's the transitive condition. Then the congruence relation is an example of an equivalence relation. Now the equivalence classes start with R being an equivalence relation on a set A. The set of all elements that are related to A is called the equivalence class of A. The equivalence classes now will give us a partition, but طبعا we can first of all we write the class of A. This is the set of all elements related to A. We write it in a bracket and write the name of the relation. This would indicate the equivalence class of A. By definition, then the equivalence class of A will be all S such that A is related to S. طبعا this is all the elements that are related to S. This is called the equivalence class of A. طبعا if the relation is known, we can just write the element in a bracket to indicate the class of A if the relation is already known. Let's look at an example of equivalence classes. For example, in the congruence modulo 4, what are the class of 0, for example, or the class of 1? The class of 0 in the congruence mod 4 are all the numbers that are congruent to 0. So that means that those numbers are divisible by 4. All the numbers A that are congruent to 0, that means they are divisible by 4. So here is the class of 0. It includes طبعا all the multiples of 4. It includes 0, 4, 8, and also the negative numbers, all the numbers that are divisible by 4. What about 1? The class of 1 are all those numbers A which are congruent to 1. That means A minus 1 is divisible by 4. These are the numbers 1, 5, 9, and also the negative numbers minus 3, minus 7. Every number such that if you subtract 1, you get a number divisible by 4. This is the class of 1. In fact, there is only in congruence modulo 4, there is only 4 classes. The equivalence classes will give you a partition. A partition, this is now back to set theory. A partition of a set is a collection of disjoint non-empty subsets that have S as their union. These sets are non-empty, they are disjoint. If you take the union of all these sets, you get the set you started with, S. This is called a partition. Here is an example, a picture of a partition, and here are the conditions. You want non-empty sets, and you want them to be pairwise disjoint, meaning they have nothing in common, and their union must give you the entire set. It turns out that the equivalence classes will give you a partition. And here we are back to the example of the congruence mod 4. We've already listed the class of 0, the class of 1. The class of 2 will be all the numbers such that if you subtract 2, you get a number divisible by 4. Here is the class of 2 listed. Here is the class of 3, which is all the numbers such that if you subtract 3, you get a number divisible by 4. Now every integer must be in one of those equivalence classes. And if you divide any integer by 4, the remainder will be one of these numbers, 0, 1, 2, or 3. And therefore, every integer will be congruent to one of those numbers. Every element, every number will be in one of those equivalence classes. These 4 classes will form a partition. First of all, it's clear that they are disjoint. If you take their union, that will give you all of the set of integers, but then they will form a partition for the set of integers. Next, we would like to cover partial ordering. A relation on a set is called a partial ordering or a partial order if it has the three properties reflexive, antisymmetric, and transitive. If you have a set S with a partial ordering R, then the pair will be called partially ordered set, or a poset for short. And you can write it as an ordered pair S and the relation R that gives it the partial order. Members of S are called elements of the poset. Here is, we have actually many examples of partial orders. The relation greater than or equal is, we can easily show it is a partial order on the set of integers. Reflexivity is immediate. Every element is greater than or equal to itself, and that gives you reflexive. If A is greater than or equal to B, and B is greater than or equal to A, then طبعا we know about real numbers or the set of integers. If that's the case, then A must equal to B, and that is the property of antisymmetric. Transitivity is easy. If A is greater than or equal to B, B is greater than or equal to C, then A will be greater than or equal to C. Then greater than or equal is a partial order. If you take Z with the greater than or equal relation, that is a poset. Greater than or equal is a relation that will define a partial order on the set of integers. Another relation that we looked at is the division. With the division, you have to restrict it to the set of positive integers, and you cannot divide by 0. Then the relation divide on the set of positive integers, Z plus, is a partial order. Reflexive is also easy. Every integer divides itself for every positive integer. That gives you reflexive. If A divides B and B divides A, then A equal B. And that is the antisymmetry. Also, the transitive property follows from one of the rules we looked at when we studied division. If A divides B and B divides C, then A divides C. That is the transitive property. Then Z plus with the relation divide is another example of a poset, a partially ordered set. Another relation is the subset relation, the inclusion. This is a partial ordering in the power set on the power set S. طبعا subset relation, the way to show that it is a partial order, reflexive property, every set is a subset of itself. Every set is related to itself. But that gives you that the relation is reflexive. Antisymmetric, if A is a subset of B and B is a subset of A, then A equals B. But that gives you the antisymmetric property. Transitivity, if A is a subset of B, B is a subset of C, then A is a subset of C. Then the relation subset is a partial order on the power set of a set A. We have more definitions. Two elements. طبعا احنا here we are using the what looks like the relation less than or equal, but this can be used for any relation. If A and B are elements of a poset, poset طبعا is a set with a partial order. Here we're using what looks like less than or equal, but as I said, you could use any partial order. If two elements are comparable, if either A is related to B or B is related to A. For example, if you are taking less than or equal, then two elements are comparable if either A is less than or equal to B or B is less than or equal to A. Okay. طبعا if A and B are such that neither of these conditions holds, then they are not comparable, incomparable. Here are examples in Z plus with division. We already know that this is a partial order. 3 and 9 are comparable because 3 divides 9. But 5 and 7 are not comparable. They are incomparable because 5 does not divide 7 and 7 does not divide 5. If you have a partially ordered set such that every two elements are comparable, this is called the totally ordered set or linearly ordered. The order that gives you that partial order is called now a total order or a linear order. Sometimes a totally ordered set is called a chain because you can order the elements what would be like a chain. Every two elements are comparable, so you can list them in a certain order, like a chain. We have examples of total order. The poset Z with the relation less than or equal, we already showed that it is a partial order. This is totally ordered, and any two elements, if you take any two elements A and B in Z, then one of them must be less than or equal to the other. So either A is less than or equal to B, or B is less than or equal to A. This is something we know about real numbers, in general, in particular, for any two integers, one of the integers must be less than or equal to the other. But this is an example of a total order. But Z plus with division is not total order because we have already given an example, 5 and 7. These are not comparable. Total order, every two elements must be comparable. For Z plus with divide, there is at least two elements that are not comparable, 5 and 7, but this is not a total order. Next, we would like to look at Hasse diagrams. Hasse diagrams is just a diagram for partial order. That is done in a more compact way. We do it in a way that the graph is more compact. Sometimes with a relation, if you try to draw all the edges in the graph, in the graph that represents the relation, you'll have too many edges. The Hasse diagram is just a way to graph the relation in a compact way. The best way to do this is to look at a graph and see how you can form the Hasse diagrams. So let's look at a graph, an example, and see how we can form a Hasse diagram. So this is now for the relation less than or equal for the set on the set 1, 2, 3, 4. The graph in part A is the graph for that relation with all the edges drawn. You see the loops. The loops in this relation means every number is less than or equal to itself. There is also every possible ordered pair in the relation, there is an edge drawn. For example, 1 is less than or equal to 3, 1 is less than or equal to 2. For every possible pair is ordered there. Here is now what we do to form a Hasse diagram. The first thing we do is we remove all the loops. Now we don't need them. We know that a Hasse diagram is for a partial order, so we know that every element is related to itself. So that's the first thing we do, is remove the loops. We end up with graph in part B. The next thing we do is we remove any edge that's not needed. For example, since 1 is less than 2, less than or equal to 2, and 2 is less than or equal to 3, we don't need the edge from 1 to 3 because we know that the graph is transitive. There are many cases here where an edge is not necessary because the knowledge in this is a partial order, so it's transitive, so some other edges can be removed without loss of information. So we remove the edges that are not needed due to the property of transitive. The last thing we do is we list the elements so that every element is less than or equal to the one above it. Yani we list them in order. List the 1 first, then on top of it 2, then 3, and then 4. And here you don't need the edges. You don't need the direction, because you know that 1 would be less than or equal to 2, 2 is less than or equal to 3, 3 is less than or equal to 4. So the direction here is removed. The last graph in C is what's called the Hasse diagram for this relation. It is just a compact graph for the relation where loops are removed, where any edge that's not needed because of the transitivity is also removed, and finally the direction is removed by listing the elements where every element is smaller than the one above it. Then you can remove the direction and you end up with this compact drawing. This last drawing is called the Hasse diagram for this given relation. Okay, we have more definition, maximal and minimal elements. Elements of the posets have certain extremal property that are important for many applications. For example, what do we mean by a maximal element? A poset now again is a set with some kind of partial order defined on it. An element is called maximal if it is not less than any element of the poset. That doesn't mean that it has to be larger than any set. It does not have to be larger than all the other elements, but there is no element in the set that's larger than this element. You can do it more precisely. A is called maximal afwan. This is different than maximum. This is maximal if there is no B in the set such that B is larger than A. It is called maximal. What about minimal? Minimal, that means there is nothing in the set that's less than the element. If it is not greater than any element of the poset. A is minimal if there is no element B in S such that B is less than or equal to A. Maximal and minimal elements are easy to spot in the Hasse diagram. The top elements are the maximal elements and the bottom ones are the minimal elements. Here is an example. This is for the set 2, 4, 5, 10, 12, 20, and 25 with the relation divide. The Hasse diagram is to the right. What are the maximal elements? These are the one on top. The elements 12, 20, and 25 are maximal. There is nothing above them in the graph. There is nothing that is divisible by 12 or divisible by 20 or divisible by 25. That makes those elements maximal. What about the minimal elements? These are 2 and 5. There is nothing below them in the graph. That means there is nothing that divides 2 from the set. There is nothing that divides 5. That makes them minimal elements. This example shows that a poset may have more than one maximal element, and it also may have more than one minimal elements. We have more definitions. We say that A is the greatest element of a poset if B is less than A for all B in S. A has to be larger than any elements in S. Now notice this is different than maximal. That means A must be related to all these elements in S and it must be larger. Greatest element, if they exist, they will be unique. There will be only one element that is the greatest. What about least elements? Again, in a poset, A is the least element if A is less than or equal to B for all B in S. And what that says, that A is related to every element in S, and it is less than any element in S. Like greatest elements, the least elements are unique. If there is one, there is only one. Here are examples. The one أول شيء part A. What are طبعا عندنا there is no greatest elements. but A, the vertex A, is the least element. It is less than anything else in the set. In graph B, there is no maximal element, قصدي no greatest element and no least element. In C, there is a greatest element, which is D, but there is no least element. In graph D, D is the greatest element and A is the least element. More definition, and all of this طبعا is related to order. If you have a subset A of a poset, U is an element of S such that A is less than or equal to U for all elements A in the set, then U is called an upper bound. Notice that يعني A may not be in the set. عفوا يعني A the upper bound does not necessarily يعني have to be in the set itself, but an upper bound has to be larger than any other element in A. This is called an upper bound. طبعا what the element look like, what the upper bound look like, depends on the relation, but it has to be something larger than anything else in the set. طبعا there could be more than one upper bound. The smallest is called the least upper bound. The element X is called the least upper bound of a subset A if X طبعا has to be an upper bound and it is less than every other upper bound of A. We will look at an example. Now, what about lower bounds? طبعا a lower bound has to be something less than all the elements in the set. This is called a lower bound. There could be more than one. The greatest lower bound is يعني the upper bound, the lower bound that is larger than any other lower bound. فإذا A is called a lower bound, a greatest lower bound if it is a lower bound and if it's greater than any other lower bound. The greatest lower bound and least upper bounds of a subset A are denoted by GLB for greatest lower bound, LUB for least upper bound. But we will look at an example. طبعا all of these elements depend on how the order, the partial order is defined. Here is an example. This is again this set with divide relation, and here is the graph. We want to find lower and upper bounds for this set A equal 2 and 4. Remember now we are working with the divide. For a lower bound, for example, would be a number that divides both 2 and 4. The only number that does that is the number 2. Now what about an upper bound? An upper bound has to be a number that's divisible by both 2 and by 4. So we want now the greatest lower bounds for A and the least upper bound. The only lower bound for A is 2 because it's the only number that divides both 2 and 4. For the greatest lower bound, since there's only one, will also be 2. What about upper bounds for the same set? An upper bound now has to be something greater than 2 and greater than 4. In this partial order, that means it has to be something divisible by 2 and divisible by 4. So there is 2 lower bounds, actually several upper bounds, 4, 12, and 20. All of these are upper bounds because they're divisible by 2 and divisible by 4. Now what is the least upper bound? It would have to be 4. Then 4 divides 12 and 4 divides 20. It is, in that sense, it is the smallest upper bound. Then the least upper bound for A is the number 4. There's 3 upper bounds, 4, 12, and 20. The least of these numbers is 4. طبعا least in the sense of divide. 4 divides all the other numbers, but that makes it the smallest.